Hello everyone, welcome back. Today we're going to begin with chapter in the lecture 25th. It's a new chapter on alcohols, ethers, and epoxides. I believe that you had a good understanding and a good exercise in lectures 22, 23, 24, which deals with mostly alkenes. Alkenes are functional groups that have a double bond. Now, in this new chapter, we're going to discuss alcohols, ethers, and epoxides. These are oxygen-containing functional groups. Functional groups are very important, and this would help you broaden your understanding of most of organic chemistry concepts. But here in this chapter, alcohols, ethers, and epoxides, which are oxygen-containing compounds in general, as a functional group, would be discussed. So, when it comes to alcohols, for example, the first, what you see is it is characterized by having an OH functional group. So the functional group is OH. So if you have a carbon, which is an alkyl group, that's what's the R group is all the alkyl chains that is possible. But the most important part of an alcohol is all. So the names always also contain all in their ending. So this is an all or alcohol functional group, which is an OH in organic compounds. So whenever you see an OH group in organic compounds, that is a functional group that acts as an alcohol. So they have their own properties and all that. So before we go in detail about alcohols, they have also characterized by what we know. For example, if it is a simplest alcohol, which has only 3 hydrogens and 1 carbon, it's called methyl alcohol. So that is the smallest alcohol that you could have. So these are called a methyl alcohol. So that is the smallest one. But after that, whenever you have more carbons in the structure, you would have a primary, secondary, or tertiary. Remember back, we have a primary alkyl halide, a secondary alkyl halide, a tertiary alkyl halide. In the same context, alcohols also have a primary, secondary, tertiary. Methyl obviously is just CH3OH. So this is a CH3OH methyl alcohol. It actually is called also methyl alcohol. So in the primary alcohol, it has only it is attached to a carbon which is only attached to 1 carbon. So this carbon, which contains the OH, is attached only 1 carbon. The rest are hydrogens. The 2 remaining groups are hydrogens. But in secondary alcohols, which are more crowded now, you have the carbon that contains the OH group is attached to 2 carbons. These R groups are the carbons, other chains of carbon, but only 1 hydrogen on that carbon. So that's a secondary alcohol. A tertiary alcohol, which is the most crowded one, has 3 alkyl chains substituted to that carbon. Hence, it is a tertiary. So remember now, the nature of the alcohol is important in the future when we study bonding, chemical reactivity, solubility, and all properties are depending upon whether you have a primary, secondary, or tertiary alcohols. So the carbons that are in these alcohols so far, what we discussed is sp3 hybridized. That means they are attached to 4 different things. So the carbon that is contained in the secondary is also sp3. Here is sp3 hybridized. So the hybridization of these alcohols is sp3. But there are special type of alcohols as well. So for example, if an alcohol is in aromatic ring, which we will discuss in Org 2, it is called a phenol. So this is phenolic alcohol, phenol. That means this is a phenyl group, and the alcohol is designated by ol, so it's a phenol compound. Still, it is an alcohol nature, but it is attached to an sp2 hybridized carbon, different from sp3 hybridized carbons. That is called a phenol. And there are also, if you have this is an alkene, and directly where OH is attached on sp2 carbon, it's called vinyl alcohol. This is a vinyl alcohol. So it reacts differently because if you remember in our previous discussion for alkyl halides, we had vinyl halides. For example, NX there is phenyl halides, vinyl halides. For the alcohol, it's called vinyl alcohol. For example, if we were to have in alkyl halide studies, for example, if you have bromine, this is vinyl bromide. So these are different kind of alcohols. That is the main point. They react differently because the reason that they are attached to a different carbon makes them to react differently. So we will mainly focus now on sp3 hybridized carbon that contains OH group. So those are primary, secondary, tertiary alcohols. So these are special cases of an alcohol. Moving on, ethers, instead of having an H, that H is replaced by another carbon. So it is a ROR, meaning that if you have an R alkyl group in this side, and the OH is also replaced by, instead of H, if it is another alkyl group, they will be called ether functional group. Ethers are ROR, meaning that you have an alkyl group, oxygen as a bridge between the two alkyls, it's always there as a center, and you have another alkyl group. For example, if you have a methyl group and another methyl and oxygen there, this is called dimethyl ether. Dimethyl ether. So ethers can be symmetrical or unsymmetrical. What I mean is it could have the same substituents across the oxygen. In that case, it is symmetrical. But in some cases, one side would be a different alkyl chain and the other side would be a different one. For example, you have here ethyl methyl ether. So this is called ethyl, which is this, methyl, this, ether. In this case, since our group are not the same, like this, R and RO are different. When R and R are different, that is when ethyl is different from methyl, these are unsymmetrical ether, when they are not the same. This is just a structural description of this. So ethers are, it could be any kind of alkyl chain bridged by oxygen and another alkyl rather than H. So in alcohol, one side is an OH, not OR, but here an OH, so that becomes an ether in this case, ROR. Okay, let's move on another one. Moving on to another functional group, they are called epoxides. They are like ethers, but cyclic one. They are a three-membered ring. That means you have R, O, R, and bridged. That means a three-membered where oxygen is one of the atom group. They are called epoxides. Epoxides are also the same, that is sp3 carbon is here, another sp3 carbon. So they are three-membered. Always epoxides are three-member rings when one of the group that makes the bridge is an oxygen. They are also sometimes called oxiranes. So epoxides, ethers, and alcohols. So in the most cases, they have dipole moment because of the oxygen. So that dipole moment makes them some relatively more polar in some cases. So we'll see in detail what the different chemical property and physical properties, starting with an alcohol. So we'll go to the ethers and epoxides later on. But this is just a general overview of what an alcohol is, what an ether functional group is, and what an epoxide is. So in the next series, I will show you in detail each one of this functional group, and this is a new chapter that contains these three functional groups. So it will be a very long chapter, but we'll have a very important discussion that will help you understand functional groups that are oxygen containing, and also the different varieties, alcohols, ethers, and epoxides. So now when we discussed alcohols, we start from the structure and bonding in alcohols. So mainly we focus where the oxygen is. So in sp3 hybridized, or in the alphabetic chain one, the oxygen is also sp3 hybridized. So that means sp3 hybridized, for example, in methanol, CH3OH is methanol. The oxygen and the carbon, all of them are sp3 hybridized. When you are sp3 hybridized, you have 4 orbitals. That means in this, if I draw it out, oxygen as sp3 hybridized orbital, it has sp3 for this, and hydrogen, that is sigma, sp3h, and with the carbon, which has sp3 as well, so the oxygen is bonded as sp3 sigma bond, sp3 oxygen, and bonded to sp3 carbon, which is this carbon, this one, and hydrogens are sp3, as I said, has 4 orbitals. That means the 2 remaining sp3s are this. So this is how it looks like, the bonding orbital. So that means lone pair of electrons, 2 pair of electrons are in one of the sp3, in one of the sp3. This up and down, that's what I'm just showing here. Rather, I can just show them here, here. So those 2 lone pairs are in sp3 orbital as well, but the bonding, the sigma bond, is sp3, sp3s sigma. This is also sp3, sp3 sigma. That's how the bonding looks like. So the main important point here is oxygen in alcohols, especially in aliphatic alcohols, it is sp3 hybridized. So the oxygen, as general, you should know, it is sp3 hybridized. So the bond angle between this carbon and that hydrogen, meaning the center would be oxygen, is 109 degrees. For carbon as well, if you remember, CH4, methane, has also 109 degrees of hybrid orbitals. So that's important to note, that it is the same as the carbon in terms of its hybridization. It is 4 lobes, or 4 molecular atomic orbitals to that oxygen. And the other important thing you need to remember would be CH3, for example, OH. There is a dipole moment, meaning that there is a dipole that is created. That means it has this dipole, meaning that this is relatively positive carbon because electrons are withdrawn by this more electronegative atom, so oxygen is relatively electronegative. Here also the dipole moment might be not much as long as this, but the electronic difference would be this is relatively a sigma plus and the oxygen is a sigma. So it has a dipole. So oxygen, in alcohols, all of the compounds have a dipole moment. So that makes them polar also. So remember, so the dipole makes them polar molecules. So alcohols are polar molecules, like water is a polar molecule because water is, rather than ROH, it is HOH. So it has a dipole moment of like this and like that, so like this. So there is a net dipole moment upwards. So this is polar. So like water, organic alcohols have also some polarity in them. So they are more polar molecules. So they dissolve in polar solvents. So alcohols are polar molecules. They dissolve more polar molecules. So that's how the structure looks like. So by having an hydrogen that is attached to oxygen, which is more electronegative, they also make hydrogen bonding. We have just said dipole-dipole interaction can have between those molecules, meaning that if you have one molecule of methanol with another molecule of methanol, it has a dipole-dipole interaction, intermolecular force. So the IMF, intermolecular forces, IMF we call them, is the most important one. Maybe the larger or stronger one is hydrogen bonding, because they hydrogen bond between each molecule. And there is also a weaker dipole-dipole moment. So in general, this makes them to have a higher boiling point. The reason why, for example, between hexane, which doesn't have any oxygen or hydrogen in it, and hexanol would have a higher boiling point because it has hydrogen bonding and a dipole-dipole. So in general, why they have higher boiling point, alcohols? Because their intermolecular force between them, between each molecule, is contributing of hydrogen bonding and also dipole-dipole interaction. For example, if I draw hydrogen bonding for methanol, if you have CH3OH, another molecule of the methanol would be making hydrogen bonding. This is H, this is oxygen, CH3. Here with this one, hydrogen would make hydrogen bonding with oxygen. This is CH3, H. So this would make hydrogen bonding with another oxygen, CH3, H, and so on. So this is the intermolecular force that exists in alcohol that makes them to make a hydrogen bonding. In the future, you'll see that a primary alcohol is much easier to make hydrogen bonding than a tertiary alcohol because there is a steric hindrance to reach to that OH group. So this is very important. The nature of the alcohol, we'll see their higher boiling point in the primary alcohol versus tertiary alcohol or secondary alcohol for that matter. But in general, in the nutshell, what I'm trying to tell you here is a very important concept why alcohols have higher boiling point. Because they make hydrogen bonding like this, and there is a dipole-dipole, meaning that this negative one would interact with positive of this. So there is a weaker dipole-dipole plus hydrogen bonding. The combination of the two makes them to have higher boiling point. Okay, let's move on in general in naming. How do we name alcohols in organic compounds? There are common names which we don't we use for common alcohols, but not every alcohol has common name. For example, isopropanol. This is a rubbing alcohol which you find in pharmacies and all that. So this isopropanol is a propanol because 1, 2, 3 carbon is a propanol, and the position of the OH is at the center carbon. That's why it's called iso. You could say just propanol by just 1, 2, 3. This is just propanol. But this one is isopropanol because the OH is at the center. Isopropanol. So if you were to name it systematically or scientifically or IUPAC naming, it will be 2-propanol also. Because always the priority for counting would be alcohol, OH group. So you have 1, 2. 1, 2. So it is a 2-propanol also. Always the priority in naming OH comes first. Another one, which is called tertbutanol. Tertbutanol is a tertiary alcohol, a very bulky alcohol. We call it tertbutanol. So that is a tertiary. This is a secondary alcohol. This is a tertiary alcohol. This is a primary alcohol. But in any case, that is a tertiary butanol. So it is at 2 position. So if we're systematically to name this, so we could name this, the straight chain is 1, 2, 3. At 2 position I have methanol, alcohol, so it will be a 2 position. At 2 position I have also metal group, so it will be 2 metal, 2 propanol. 2 metal, 2 propanol. Alphabetically, you have to put it that way. So that is 2 metal, 2 propanol. But the common names are, some alcohol, as I told you, have just a common name, like ethanol, methanol, propanol, tertbutanol. At least the lower molecular weight alcohols have common names. If we're to name this, here you see here, it is a 1, 2 position, there is methanol. But you don't start from this side because always the priority would be for alcohol. So if I start from here, 1, 2, 3, 4, you don't call it a 4. So you start from the other side where you get the lowest number for the OH. So this is a 3 and a 5 metal. So this is a 5 metal, 3 hexanol. 1, 2, 3, 4, 5, 6. Hexanol. This is how you name it. Okay? Metal 3 hexanol. Okay. So the priority is always for OH versus metal group, alkyl group. So that's the functional group. That actually tells you your main functional group is alcohol, all. So all of alcohols end with the name OL, all. Tertbutanol, isopropanol, 2-propanol, 5-methyl-3-hexanol. So if whenever it sounds like OL, it's all, that is an alcohol. So that's how you'd understand, oh, it's an alcohol. Okay, I have also here a compound which is named as 2,5,5-trimethyl-cyclohexanol. So here, this is a 1 position, always. In the ring where the OH is, that is a 1 position. Therefore, at 2 position, you don't go like this, because there is a substituent here. So you always want to minimize the numbering. So you don't go this way because this would give it a higher, larger number. So I go this way. This is a 2 metal, 3, 4. At 5 position, I have another metal, 2 metals actually. So it would be a 2, 5, 5 dimetal, trimetal actually. All are metal groups, so it would be trimetal, cyclo, it is a cyclic, hexanol. Remember the OL, that is 255, meaning that at 2 position I have metal, at 5 position I have metal, at 5 metal I have, so it is a trimetal, 3 of them, trimetal, cyclohexanol. So I really encourage you, because I will have this in most tests and quizzes, how to name different alcohols. Here in this case, this is much easier. This is at 1 position I have my alcohol, and at 3 position I have metal. So this would be just 3 metal, cyclo. You don't have to say 1 hexanol. It is already understood that at 3 position there is metal, therefore at 1 position it should be an alcohol. So a priority in naming always goes for OH whenever you have different functional groups. So we'll practice that more in the next section. So this is an overview of how alcohols are bonded. They are sp3 hybridized. They have dipole moments. They make hydrogen bonding, hence they have higher boiling point. There are common names of some small alcohols, and priority for naming would come for OH as the lowest numbering. So all, that tells you it's an alcohol. So that's the naming we'll be adopting from now on. All right. Let's further discuss some naming of the alcohols, common alcohols, and some of their characters in the ones you see here on the board. So, for example, there are diols, meaning that you have 2 alcohols. This is commonly known as the antifreeze ethylene glycol. This is a common name for this, is just common name, not scientific. We call it ethylene because it has 2 carbon, glycol. So this is because they have 2 of them. But if you were to name it in terms of like the IUPAC naming, it will be a 1 and 2 position you have OH. So it will be 1, 2, ethane diol, di, 2, all the alcohols. So this would be 1, 2, ethane diol. So this is a common alcohol used in antifreeze or also in the radiators of the engines. So if you see this ethylene glycol would be much higher in boiling point. Now I'm just giving you some ideas based on your knowledge. If I were to ask you ethanol versus ethylene glycol, if I ask you the boiling point, you don't have to remember the numbers, which one would be boiled at higher temperature. So ethanol, which has only 1 OH, it can make only one side, the hydrogen bonding, but ethylene glycol would have multi-hydrogen bonding. So obviously ethanol boils around 72, 70 something, but ethylene glycol must be boiling at higher temperature than ethanol. So higher temperature because it has more hydrogen bonding possibilities for ethylene glycol. The next alcohol it is a triol because it has 3 hydroxy groups. So the 3 hydroxy groups makes it a triol. So, but this is a 3 carbon hydroxyl. If any one of you taking biochemistry, this is a glycerol compound. So the common name is just, if you're not scientifically explaining this, you could just call it glycerol. Glycerol is a 3-carbon triol. Obviously, this would have also a very high boiling point. Probably this is very viscous as well. So this is glycerol, but if you were to name this, it would be a 1, 2, 3, a 1 position, a 2 position, a 3 position hydroxy. So it would be a 1, 2, 3 propane triol, propane triol. Propane because it is a 3-carbon, and it's triol because it has 1 oxygen, 1 hydroxy here, 1 functional group here, 1 alcohol here. So that would be a triol. This is a diol. So this is glycerol, but the IUPAC naming, the systematic naming, which mostly organic chemists use, is called 1,2,3 propane triol. Here it's 1,2-ethane diol because it has 2 carbons. Here there is 3 carbons. Okay, and the one you see here also is named as, here the stereochemistry is also mentioned. It's not in the RS terms, but since the OHs are in opposite direction, one is down and the other is up, so this is trans 1,2 cyclohexane pentanediol. It should be cyclopentanediol. Di because it has 2 hydroxys, all obviously the alcohol, and they are at 1 and 2 position. So they are neighbors. In 1, 2 position is where they are. Trans refers to up and down. So they are in the cyclopentanediol. Here we have a very long chain, so you have to find first the longest chain in the system. This is obviously, this is the longest chain, meaning that if you start from here, 1, 2, 3, so you should always include the OH because that's where the priority comes from. So you have to always count a chain that contains the high priority functional group. So if I count here 1, 2, 3, it would put the hydroxy or the alcohol functional at 3 position. It's 1, 2, 3, 4, 5. At 5 position I have an ethyl group. At 6 position I have methyl group. So that would be the naming will follow. This is a nonane compound because it's a 9 carbon. So the naming would be a 5-ethyl, which is called, and spelling also starts with 5-ethyl, 6-methyl, and 3-nonanol. Nonane, okay, so it's a 3 position. Okay, 5-ethyl, 6-methyl, and alphabetically this is how you should write. Ethyl comes first before, ethyl comes first and methyl the second one. So the alcohol is a base, so it should come later. So that is a 5-ethyl, 6-methyl, 3-nonanol compound. Nonanol because it is a 9 carbon. Nonane, it came, the root is nonane. Nonane is a 9 carbon. Is 10 carbon, and so on. You should remember from your alkanes chapter. Okay, let's see this one as well. If we were to count, we should count from here. By the way, I want to label each one of them. So for example, in ethylene glycol, this is both of them are primary alcohols, primary, because they are attached to 1 carbon and 1 carbon. Here, this OH is attached to only a carbon, that's to only one carbon, which is attached to one carbon. So this is a primary alcohol. This is primary, and this is primary as well, but this one is secondary alcohol. So glycerol has two primary alcohols and one secondary. The secondary one is because it's in a carbon that's attached to two carbons. Okay, here this alcohol is a primary, by the way, because it has attached only to one carbon. Okay, let's start as this is at one position, so you don't have to mention anything about one. Is we know it's tip. So this is one carbon, two carbon, three. At three position, I have two metals, so it is a 3,3 dimethyl. 3,3 dimethyl, but 1, 2, 3, 4, 5. So it's a pentanol. 3,3 dimethyl pentanol. Pentanol. 3,3 dimethyl pentanol, because it is pentanol without specifying whether the alcohol is at one position. You don't have to, because it already is automatically known the alcohol is at one position if you are three. So 1, 2, 3 is 3,3 dimethyl. Okay, let me see this one here. You have an alcohol function, that is a one position. This is a cyclohexane ring. These are the substituents. So if I count from here like this would be a two position. At two position, I have two tertiary group. This is tertiary butyl group. That's a substituent. Tertiary butyl group. So that would be two butyl, and three methyl, and it is cyclohexane. So the naming for this is two butyl, two position, a three position methyl. So this is two, this is three, two butyl, three methyl, cyclohexane. So this is basically how the naming goes, and these are some common alcohols like ethylene glycol and glycerol. And with scientific naming for alcohol, I encourage you to practice alcohol namings as a functional group. So we'll continue more on the properties of alcohols. So here I'm continuing to discuss some summary on hydrogen bonding, and the nature of the alcohols is important. Hydrogen bonding is a property of any hydrogen that is attached to electronegative atom would produce hydrogen bonding. So for example, in methanol, for example, this hydrogen is attached to a more electronegative atom. Hence, that has a potential to make hydrogen bonding. So the structure of the hydrogen bonding looks like this. So the O, because of its partially negative dipole, and this is partially positive, they interact. Here is negative, here is, so this is, and so on. So this is sigma negative as well. So hydrogen bonding is intermolecular force that would increase. As it increases, it would create a different kind of physical property. Mainly, the boiling point of a compound would increase if there is a high possibility of making hydrogen bonding. So in general, hydrogen bonding increases with the nature of the alcohol. Here, for example, a tertiary alcohol, because of its very branched and bulky 3R groups from different size, that is not very easy to make compact hydrogen bonding. So it's the weakest hydrogen bonding. The second one, because you have two alkyl groups and one hydrogen, that's a secondary one. So a secondary would be a much higher boiling point than a tertiary. So if you are asked to just classify without knowing 3 different alcohols with 3 different positions of the OH, meaning that a primary, secondary, tertiary, you would arrange in the order of this. So the highest boiling point would be a primary alcohol because it is at the tip of the alkyl, it's not on the branch. Therefore, it is easier for it to make this compact molecular structure. So this is highest boiling point, highest hydrogen bonding, and also highest boiling point for the same number of carbon, of course. You have to compare apples with the apples. So if you have the same number of total carbons, but the nature of the branching or where the alcohol is residing, that would make a difference in boiling point. Here I have a good example. Look at this example. This is a 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, basically all 4 carbon alcohols. These are all ROHs, alcohols, functional group. And their boiling point is, as you see, is 83, 98, 118. So there is a scientific explanation or organic chemistry, or there is a physical property, which is intermolecular force due to hydrogen bonding. Those boiling points are predicted. So if I just ask you, why is this boiling point trained? Immediately you would say, oh, hydrogen bonding. What's the hydrogen bonding, the nature of it? This is tertiary. Not very good in making a compact because of this alkyl, especially when they become larger group. It cannot come closer because of the sterics. So sterics is important, steric factor, to make the hydrogen bonding. Hence, this is the weakest hydrogen bonding. The second one is secondary. It's 98 degrees. It's much better. It can make the hydrogen bonding because the groups are 1, 2 alkyl groups. This and these are the alkyl groups. Here you have 3 alkyl groups. One is hydrogen in this one. And in this case, you have only, if you just rewrite it like this is a primary because you have only 1 alkyl group. The 2 are small groups of hydrogen, so it is a primary one. It's much easier for it to make a hydrogen bonding. Therefore, it has 118 degrees. So we were able to explain, rationalize why those are the boiling points as indicated. So hydrogen bonding in organic compounds is very important. So you know why water has a boiling point of 100, because it has 2 hydrogens that can make a hydrogen bonding. So HOH, water, boiling point because it has a hydrogen bonding with this, hydrogen bonding with this, and so on. This, etc. So it's intermolecularly weaved, so it has a higher boiling point of 100 degrees Celsius. But we were discussing organic compounds. So alcohols also have higher boiling points, like water, because the hydrogen bonding that could be made in these molecules. And remember, the more branched you have, meaning that the tertiary is much weaker hydrogen bonding maker, secondary is better, the primary one is the best hydrogen bonding possibilities with that compound. So normal butanol, 1, 2, 3, 4, this is N-butanol. Normal butanol is at higher 118. This is 2-butanol at 2 position. This is 2-butanol. That is N-butanol. This is 2-butanol. This is tertiary butanol. So the boiling point trend looks like that. So With this, we'll continue more in this chapter next time.